In this section, we're going to look at infinite limits and limits at infinity. So first, let's look at this very basic 1 over x graph, this rational function. So if we recall from Algebra 2, we know that there are two asymptotes. First, we have the vertical asymptote. And you can see that vertical asymptote is this invisible vertical line that the graph cannot pass through. We call that vertical asymptote, and that is at x equals 0. The second one is the horizontal asymptote. And that is this invisible red line, and this one is at y equals 0. For horizontal asymptote, though, we did say in Algebra 2 that it could cross the horizontal asymptote when it's close to the origin, but not so when it's in infinity, and we'll talk about why. So now that we're in calculus, we are not going to define vertical and horizontal asymptote this way anymore. We're going to define them using calculus terms, which is limit. So first thing is the vertical asymptote. So the vertical line x equals a is called vertical asymptote. On the graph f of x, y equals if, okay, so now let's kind of look at this graph. So when you have the vertical asymptote x equals 0, what's going on around that asymptote? Well, you can see that the graph from the left-hand side and the right-hand side are going somewhere. And then when we're close to that vertical asymptote, the graph is going to infinity, right? Either it goes up to infinity or it goes down to negative infinity. So what we want to do is write a limit notation that represents that, saying that when the graphs are going to a certain number, the two sides of that graph is going to infinity or negative infinity. And so by definition, the vertical asymptote is saying when the limit as x goes to a number from the left-hand side, the y value, or f of x, is going to infinity or minus infinity. It doesn't have to be, it cannot be both, obviously. It just has to be either one. Or the limit as x goes to a from the positive side, so right-hand side of that number, y is going to plus or minus infinity. So either one of those conditions, if it's met, then we call that vertical asymptote. Oops. Now let's talk about horizontal asymptote. Horizontal asymptote is a little different, right? So what defines a vertical asymptote? Well, let's look at this graph. So what happens is when our graph is going to the right-hand side, it eventually converges to a number, like it's getting close to a number. And so on the left-hand side, it's the same thing. When it's going to negative infinity, when x is going to negative infinity, y is getting closer and closer to some number. And so that is how we're going to define the horizontal asymptote. So we would say the horizontal line y equals, let's call it b, is called horizontal asymptote. On the graph y equals x, f of x, if limit as x goes to infinity, f of x goes to b, or limit as x goes to negative infinity, f of x goes to b. So let's talk about the similarities and differences between vertical and horizontal asymptote. First, by definition, by the limit definition, both of them have something to do with infinity, right? This is kind of the obvious part. The difference is where we're talking about the infinity. So for vertical asymptote, the infinity is in the y. So when y goes to positive negative infinity, we call that vertical asymptote. And for horizontal asymptote, that's when x is going to infinity. So when x is going to plus or minus infinity, where is y going to? So those are two different questions. All right, and just a reminder, infinity is not a value. It just means forever large or expanding out of bound. So we never say that, oh, these two limits are both going to infinity, so then they must be the same number. That is not true. We're just saying it's a very, very big number. We don't know what it is. And since it's not an actual value, we can also say that the limit does not exist. So when you're calling something a vertical asymptote, you can also say, when x is going to this number, the limit you would have said goes to infinity, or you can just say it does not exist. So let's go ahead and practice with these two problems, or we'll see if we can do two or just one. So write the asymptote using limit notation. So first, let's identify the asymptotes. We can see that the vertical asymptote here is x equals 1, and then the horizontal asymptote here is y equals 1. So then to redefine the vertical asymptote, we can say that this is limit as x goes to 1 minus f of x goes to, so when it's going to 1 minus, y is going to negative infinity, and then limit as x goes to 1 plus, which is here, f of x is going to infinity. And so that's how we define saying that, hey, there is a vertical asymptote. All right, horizontal asymptote is the same idea. So then when the graph is going to positive infinity, limit as x goes to positive infinity, y goes to 1. And then on the left-hand side, when the graph is going to, or x is going to negative infinity, y is going to 1. Now let's look at a slightly different question. Let's say that all they give you is limit and they say, please draw a graph that actually meets this requirement. Can you do it? Well, let's try it. So first it tells us that when x is going to negative 2 minus and negative 2 plus, we have some infinity. So what does that actually try to hint? When x is going to a number and y is going to infinity, remember that means vertical asymptote. So the vertical asymptote is happening at negative 2. And then it tells us that when it's going to negative 2 from the negative side, it's going up. And then when it's going to negative 2 from the positive side, it's going down. Okay, so we're just going to draw it like this for now and then try to figure out what to do with the more information. The next two things, it says when x is going to negative infinity, when x is going to infinity, and then something else happens. So remember, when x is going to infinity or negative infinity is hinting at horizontal asymptote. So we have some horizontal asymptote, or we'll see. Let's try it. So when x is going to negative infinity, y is going to negative 3. So when x is going to the left, y is going to go down to negative 3. So we have a horizontal asymptote at negative 3, like so. And then we have when x is going to infinity, y is going to infinity. So that means it doesn't have a horizontal asymptote. It just keeps going up. So this is how the graph would look like. Now that we have quickly looked at how vertical horizontal asymptotes are defined using limit notation and also how they look like on a graph, we are going to look into it deeper with just equations. How would you be able to identify the vertical and horizontal asymptote if you were just given an equation and not any kind of graph? So let's first kind of think about how can we tell when vertical asymptote will happen given an equation. So what creates the vertical asymptote? If you have a rational function like this, rational function of p of x over q of x. So vertical asymptote is whatever makes the denominator undefined. So whatever x value makes the denominator undefined is what's causing the vertical asymptote in a rational function. So that's pretty easy, and actually it's probably true for most functions that are rational in some form. So it's a very easy thing to remember. Horizontal asymptote is a little bit more difficult. So what creates a horizontal asymptote in a rational function? And I'm saying rational function because we're just going to do rational functions today, but then the next day we're going to do a much harder kind of horizontal asymptote. So if you recall back in Algebra 2, there are 3 cases where you have, horizontal asymptote. The first is when the degree of, let's make sure, okay, so the degree of p of x is the same as q of x. Okay, so if you don't recall degree, so something like, let's say 2x squared plus 1 over 3x squared minus 2. So then the degree, that highest exponent, is the same. So when that happens, the horizontal asymptote is the ratio of the leading coefficient. Okay, so in this case here, we're saying that the horizontal asymptote is 2/3 because of the leading coefficient. Okay, the second case is when the degree of the top polynomial is smaller than the degree of the bottom polynomial. So if we give an example, let's say 2x squared plus 1 again, but then in the denominator, I'm going to make it cubed instead. So then the degree on the bottom is bigger. And when that happens, we would say the horizontal asymptote is just 0. Because the bottom is expanding much faster than the top. The third case is when the degree of the top is bigger than the degree of the bottom. And then if you kind of recall from pre-calc, we said that there is no horizontal asymptote. However, there is a slant asymptote. So maybe something like 2x cubed plus 1 over 3x squared minus 2. So notice how the degree is bigger here on the top. So then that means there is no horizontal asymptote, but there is a slant asymptote. And to find a slant asymptote, you would have to use long division in this case to figure out the quotient. All right, let's do some questions really quickly. Find the asymptotes of this function. So it's pretty easy. First, find the vertical asymptote, then find the horizontal asymptote. So remember, vertical asymptote is whatever makes the denominator undefined. So that is 3. Horizontal asymptote, you look at the degrees. So the degree on the top and the degree on the bottom are both 1, which means we're in case 1. And so look at the ratio of the leading coefficient. So that is 2. Easy. All right, let's go ahead and try. Let's try this one. See if it's doable. All right, so the first thing when you see something like this is you got to factor to see if there really is a vertical asymptote. All right, so this, let's see. So this is x plus 4, x minus 2 over x plus 2, x minus 2. So then vertical asymptote is whatever makes the denominator undefined, and the horizontal asymptote is check the 3 cases. Now in this case, vertical asymptote is not everything in the denominator, because if there is a factor that cancels, that becomes a whole. So we kind of talked about it in the previous sections. This becomes a whole, and then the only thing that's left over in the denominator is the only vertical asymptote. So please be careful to make sure you factor and to identify the whole before you assume that everything in the denominator is a vertical asymptote. In the horizontal asymptote, the degrees are the same, and so we look at the leading coefficient. The leading coefficient are both 1, so this is 1. Now let's bring in some limit notation, and so don't be scared, it is not as hard as it looks. Alright, so let's look at number 1. Limit as x goes to infinity of this function. So limit as x goes to infinity is asking for what? It's asking for horizontal asymptote, right? So horizontal asymptote, and we need to kind of remember our limit rules. So limit of something minus something, or function minus function, means that we can actually just split it. And then we look at the limit. The limit of a constant function, it's just 5. And then this one is a rational function, and the rational function, you check the degree. The degree on the bottom is bigger than the top. The top doesn't even have an x, so that means the degree is 0. So the bottom is a degree that is higher than the top, which means this limit is 0. So then this whole thing is 5. We're not actually writing y equals 5 because that is unnecessary. It's just asking for the limit. The limit is 5. All right, now let's look at this one. Limit as x goes to infinity. Again, when you see this, what is it asking for? It's asking for horizontal asymptote. So now that you know it's horizontal asymptote, it's just, what is the horizontal asymptote of this? That's easy. The degrees are the same, so ratio of the leading coefficient, so that is 2. So again, don't need to write y equals 2. Okay, let's do something that's a little bit trickier. Let's try this one, number 4. Okay, so limit as x goes to negative infinity. Again, that means horizontal asymptote of this rational function. Now, in this rational function, the degree on the top is bigger than the bottom, so that means it's a slant asymptote. So there is no direct answer number. So then slant asymptote, remember slant asymptote would usually look like this. When we're talking about the two ends of the graph, your answer is either going up to infinity or negative infinity. So the question is this answer positive or negative infinity? Well, that's a little bit hard to tell. So what you can do is just put in any big number. Let's say that you change the question to like negative 100 of 3x squared minus 1 over x plus 1. So then if you just substitute that in, we don't quite care about the number itself because we know the answer would just be plus or minus infinity. We just want to know which sign. So I think you guys probably can tell. So since we have a negative number squared and that number is quite big, this is going to be a positive number. In the denominator, it is a negative number. Therefore, this limit goes to negative infinity. Okay, so let me kind of talk about that logic again. So first thing is, it's when you see this limit going to some kind of infinity, the question is, what is the horizontal asymptote? So then if you look at this rational function, you say, that is case 3, there is no horizontal asymptote. But then there is a slant asymptote, so then what is the slant asymptote telling me? Well, slant asymptote by definition means that it's slanted. And if it's slanted, then the two sides will have to go to some kind of infinity. So then we know the answer is either plus or minus infinity. So then which sign is it is really the only question we need to answer. And then so to answer the sign question, you just randomly pick a big number because all we really care about is just saying what sign is it when it's going to a very big negative number. So you plug that in and then you realize really the only thing you have to care about is the sign, and the sign tells us that it's going to be negative. Therefore, your limit is going to negative infinity. In the previous example, we looked at what happens when x is going to infinity. Now we're going to look at when x is not going to infinity, and it could be any kind of question that could happen. So let's look at this first one. When x is going to 0, well, we don't know what's going on, so the first thing we're going to do is plug it in. Well, this part is going to make things undefined, and it is not an indeterminate form because it's not 0 over 0. So what we need to do is do something else to find the limit. So we know that x is going to 0, and if we want to find the limit, we have to find the two sides of 0. So then let's say 0 minus of this function, and then we're going to 0 plus of that same function. So 0 minus, what we're going to do is just plug in a number that is close to 0 from the left hand side. So x equals negative 0.01 is probably a good choice. And then we just plug that in. And remember, what we're trying to do is not actually trying to figure out what the number is, because the number is irrelevant. We're just saying what number is it trying to get to, if there is a number. Okay, so this is 1 plus 1 over 0.0001, which becomes 1 plus 10000. That is 10,001. And so that just tells me that it's going to be a positive big number. Because you can keep picking a number that's closer and closer to 0 than the number I had picked, and your number would just become bigger and bigger. All right, so let's try this one. So when x is going to positive infinity, so then we're going to use that same number, except use a positive version. So then this is 1 plus 1 over 0.01 squared. And so we're going to get that same thing. And so that tells me it's also going to infinity. So then for this one, the limit is going to infinity for both. Okay, let me just show you one more. All right, this is an interesting one. Natural log x. Well, if you plugged in 0 in natural log x, I hope you will realize that you will get undefined. So this is something you just have to memorize. Natural log x looks like this. So when x is going to 0 from the positive side, that means we're tracing along this side. This is going to negative infinity. And this is something you just have to memorize. If you don't remember your log graph, it's impossible to do, because what are you going to evaluate natural log of 0.01? It's impossible. So you have to memorize that log graph.